All right, we're back. We are on page 318, and we're still just talking about derivatives and things related to derivatives. First derivative test, increasing, decreasing, maximums, minimums, tangent lines, whatever they throw at us now, we know how to do. So let's see if we can do this. Sketch a graph of a function with f of 0 equals 1, f of 2 equals 5. I love when you're given very specific things. So like that I can do. I'm not even going to read the rest yet. Let's just do that. So f of 0 has to be 1, 2, 3, 4, 5. Okay, so f of, oh man, and then I got that wrong. F of 0 is going to be 1, and then 2, 3, 4, 5. F of, what? I only need 2. Hold on, let's go wider. 1, 2. F of 2 is 5. Okay, perfect. We nailed that. Give us more stuff like that. All right, f prime is less than 0 when x is less than 0. So the function needs to decrease until you get to 0. And also when x is greater than 2. Okay, so f prime, so f is decreasing until you get to 0 and decreasing after 2. All right, and then f prime is greater than 0 between, okay, so between 0 and 2. So all right, so we could do, let's see, let's say we just did decreasing, increasing, and then switch to decrease. There we go. Okay, that'll do it. But like, think different, right? You don't want to always just do the most obvious thing. So what I also think I should try to do is, can I think of another graph that maybe makes this happen? So first of all, well, not first of all, but like, 1/1,000,000th of all, I don't actually know, I'm gonna move things because I decided I'm gonna do 3 graphs here. All right, so this one's gonna be quicker. Here, nope, that's the here, and then here. Okay, so I don't know if this function is nice and curvy. I don't know if it's differentiable at 0 and at 2. So like, why not? Also, that's the wrong point. Gosh, here and here. Okay, now all those things I said still apply. What if it's a straight line? Does this break any of the rules? This does not break any of the rules. That's another possibility. What about, so this, this calculus problems like this, they kind of suffer or benefit from that, like, whataboutism, like, well, what about this? What about this graph? So decreasing, oh, I have a great idea-ish. I have a great sort of idea. What if I did this, and then a little of this, and then maybe, I don't know, make the limit exist there. This. Does that break any of the rules? That does not break any of the rules. All of these are valid. Like, any of these could be the graph, and that's kind of weird. I hope I didn't get any of those wrong. I hope I read into it correctly, right? So f prime is negative, then f prime is positive. We know specific values, but we don't really know anything else. So like, yeah, I think all of these work. And that's what you want to think about. So with that in mind, let's see. Give an example showing that the following is false. Okay, so f of 0 is 4. F is a decreasing function. Then f of x equals 0 has exactly one solution. All right, so I need a counter example. So ordinarily in class, I would like ask for a lot of thoughts on this. I'm going to do something, I don't know, weird maybe. So f of 0, so let's say this is 4. F of 0 is 4. All right. So one option has exactly one. What if it has no solutions? What if our function just kind of, actually, I don't even need it to be that extreme. Let's give it a horizontal asymptote there. What about this? That's a counterexample. That's a function for which f of 0 is 4. The function is decreasing. And f of x equals 0 has no solutions. So that is a counterexample. The weirder thing that I was considering was doing something like this, like here, and then you know, like this, go open circle, go like this, go open circle, right? This function's decreasing. F of 0 is 4, assuming we label this as 4, and it has multiple solutions. So this is weird, like don't assume continuity, right? Like f of x equals 1 over x, decreasing everywhere in its domain. X equals 0 is not in its domain, but decreasing everywhere. This function I just drew, decreasing everywhere, just like a super weird kind of piecewise-ish function. You probably like throw something together using mod, M-O-D, which would potentially give you that graph. All right, if f of 0 is 4, f is an increasing function, then the equation has exactly one solution. So can I get another one that has like 0? Oh, I can. So we're gonna go for 0 on this one. So this one actually, like a standard exponential function will do that, right? So that has no solution, so that's counterexample. So this is false, yes. False, because we could make it have no solutions, and that's all you really need, right? So we could do another one of those sawtooth things that would also kind of, like it's right next to me right now. That, as long as you make it increasing, you could also do that. But I think this is good enough to say that that is false. All right, let's see. Let's do this, and then we will cut this video here. The shape of a graph. So look at the figure below. Just look at that. Okay, got it. I've looked at it. Now imagine drawing tangent lines at various points. Why imagine it? Why not just do it? Right? Like, let's see. What color should I use? I'm gonna use orange. Tangent line. There you go. Tangent line. Tangent line. So, you know, don't imagine when you can do. But I'm not going to spend my whole time going across this. So identify the intervals on which the tangent line lies above or below. Yeah, above and below. I have to do both. So this we know because we've talked about it. This is a question about concavity, really. So I'm going to use the following color for concave down. So there, that's concave down, concave down, concave down, and then I'm gonna, okay, so let's make a little key for us here. So there, that will be when concave down or the tangent line is above. And then I'm gonna switch colors, and I'm gonna use this color, and this is for concave up, tangent line below. So let's highlight those. So here, here, and here. If you draw a tangent line on any of these, on the curve at any of those intervals, the tangent line will be below the curve, which you can see between B and C definitely happen. All right, so the interval, I don't really know how to name these intervals. So where the tangent line is above, so I'm gonna say, I'm just gonna use like arrows, I guess. So like A to B, C to D, E to F. And then where the tangent line is below, it's gonna be B to C, D to E, and then F to G. Yeah, that's a bad G. G's are not my strong. Ugh. Maybe I never learned how to make a G. It's possible. So these points where the concavity is changing, where the position of the tangent line changes, these are called points of inflection. So I can fit it down here. So points where concavity changes are points of inflection. Feels like you should have an X in there, but it doesn't. Points of inflection. So all the points. So B, C, D, E, and F are all points of inflection. And we're going to come back and we're going to talk a lot more about this. So we're finally talking about concavity for real, which is good because that gives us access to like a whole new set of types of questions that we can answer. So I'm excited about that. I'll see you in the next video when we start talking about it. And I hope you join me for that. So see you then.